Okay, so this last hour or so is dedicated to multi-class classification. Okay, so one way to think about reductions is sort of in terms of the modularity that they induce. So maybe we have some kind of hairy multi-class problem, and we're going to reduce it to some sort of simple binary problem, right? Another way to think about reductions is sort of in terms of you can ask yourself, how fundamental is some bit of theory, right? And one way to measure how fundamental some bit of theory is in terms of what sort of assumptions you're making. And I guess the claim is that if you're going to make a lot of assumptions, then the theoretical statements that you're going to make, that you're going to derive from these assumptions, have kind of a limited applicability because the assumptions are very strong, right? And if you go and you look through the learning theory, just general learning theory, there are lots of different kinds of theoretical statements people make. Some of these statements make no or very weak assumptions, and they're always applicable. And other kinds of theory make very strong assumptions. And then you can make very strong statements, but you sort of have weak applicability because, in practice these assumptions maybe are not met very often. So maybe over here would be kind of the Bayesian approach to learning, where you typically assume that you have the correct prior. And then you can make some very strong statements there, which are very appealing statements. And then over here on this end, you have things like learning reductions. There's also online learning, which I think there'll be discussions of later. So these reduction statements, if you go back and you think about the theorems, they say things like, for all regression problems and for all classifiers you might learn, some particular relationship holds. This is it's kind of a weak statement because it's a relative statement. We end up saying things like a small binary regret implies a small, regression regret. This is not what you would actually want, right? What you would want is a statement which says, my learning algorithm is going to work. We're giving you some sort of substitute, which is a little bit weaker in flavor, but we're performing some trade-off. The only ways we know of, as learning theorists, the only ways we know of to really say my learning algorithm is going to work involve making more and stronger assumptions. And then the theorems themselves have a more limited range of applicability. Okay. Let's think about Snowman. Let's think about multi-class classification. So in multi-class classification, you're solving the same problem as binary classification, except there's more than two possibilities. So I guess the difference is right here. You have maybe k possible outputs. Right? So maybe tomorrow there will be thunderstorms or tornadoes or hurricanes. Or possibly multiple ones, but we won't try to do that yet. So we want to learn a multi-class classifier, which, given the features, predicts one of the k possibilities. Seems like it's a very natural problem, and maybe when you think about this, you go, I don't necessarily know how to do that with a binary classifier. But it turns out that we'll be able to do various things. So the way multi-class classification works is you're given some sort of multi-class data set. Then you want to find a multi-class classifier, which has a small error rate. Right? So the error rate is defined the same way as before. Just now that if you have 5 possibilities, you have 4 ways to go wrong, rather than just having 1 way to go wrong. Okay, so multi-class classification is the ability to solve binary classification equivalent to the ability to solve multi-class classification? It's a reasonable question. And it turns out that in some sense the answer is yes. So there's ECOC stands for Error Correcting Output Code. And the error correcting output code is a technique which has been developed to transform multi-class problems into binary problems, which you can then solve with a binary classifier, and then take these binary solutions and transform them back into a multi-class predictor. And it works in a very simple way. So we have k possible outputs. We're going to create a matrix out of zeros and ones. So I guess if it's black, then it's if it's white, then it's a 1. If it's black, then it's a 0. And then we're going to create the binary problem, which is the multi-class label. Okay, so each row is going to correspond to a 1 binary problem. And the binary problem is the multi-class label one of these 4 possibilities, right? Is it 1, 2, 3, or 5, or not? Right? So it's a simple binary question. So we can just take any multi-class sample, and we can transform it into a binary sample in this way. And we can do this for each different row, and then we can learn a classifier for each row. And then after we learn this classifier, the question is, how do we take the binary predictions of these binary classifiers that we learned and use them to make a multi-class prediction? And this is a very simple answer. Let's go back one step. So what we'll do to make multi-class predictions. So if you take a look, these binary classifiers, each individual label has kind of a canonical set of predictions associated with the binary problems. So for example, if one of the binary, if the set of binary predictions is yes, no, yes, no, yes, no, yes, no, then you'd be very tempted to say, this has to be multi-class 1. Right? And if the predictions are yes, yes, no, yes, no, 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 yes, no, then maybe you would say it's 4. Right? So the way that you actually produce the multi-class label out of the binary labels is you just compare the set of binary predictions you get, one for each individual row, to the canonical predictions that you would get for each individual label. And you see which is closest. And the way you measure closest is in terms of Hamming distance. Just what fraction of the time do the canonical predictions for each label agree with the binary predictions? All right. Now we can try to analyze this as a reduction. We can ask ourselves, how well? It seems like a sensible algorithm, right? What does this imply? Is it the case that a good binary classifier implies a good multi-class classifier? So in order to do this, we need to think about how these distributions transform. We're going to be taking a multi-class distribution. We're going to be shoving it through this error correcting output code and producing a binary distribution, right? So we have this multi-class distribution over the features across the multi-class label. And we're going to produce a binary distribution over binary samples. Ooh, excellent. and so what we're going. So this defines an induced distribution by this process, right? And how is this going to work? What does performance with respect to this induced D prime imply about multi-class performance with respect to D? So I guess this is the formal definition of how we draw a sample from D prime given the method for drawing a sample from D. First we draw the sample from D. Then we pick a random row. So the row is defined by the subset of labels which are in the set. And then we create a binary sample which is the features of the multi-class sample and the name of the subset, and then just ask, is the label in the subset or not? And so this is using that one classifier trick again. So we have a set of different binary problems, one for each row. And we're going to actually just we're going to think for the theory of learning just one classifier, where the choice of the subset is embedded into the feature space. All right. Other questions here?
John, I still don't understand the picture. So the 1, 2 up to k, they're the different classes, right?
Correct.
Now going down, are those whether a variable takes on a value 0 or 1, or what is it going?
Right. Okay. So I guess the claim is every column corresponds to a label, and every row corresponds to a binary problem. And whether or not it's solid or light corresponds to whether we're asking, is the label in the set or not? So let's go back to here. So the set defined for this row is 1, 2, 3, 5. The set defined for this row is 1, 2, 4, 6. The set defined for this row is 2, 4, 5, 7. So every row defines a subset of the labels. And the binary problem is the label in the subset or not?
So then each observation could have several different labels, is that right? So in other words, one observation could be labeled 1, 2, 3, and 5.
I see what you're saying. So when you get out the binary prediction for this row, let's say that we believe our classifier is correct. Then we're going to know that the multi-class label is either 1, 2, 3, or 5, but we won't know which. So we wouldn't. Let's say that we actually want to return some particular multi-class label, right? Then what we need to do is we need to find some way to combine the predictions of all the different rows in order to produce a multi-class label. So for example, if this row says that, yes, it's in the subset, and this row says it's in the subset, and this row says it's in the subset, and this row says it's in the subset, and all the other rows say it's not, then that would suggest that it's actually label 3, right? Because every time 3 was in the set, the classifier said yes, and otherwise it said no. So the exact way that we're going to take these binary predictions and form the multi-class prediction is by just checking to see. So we'll have a bunch of binary predictions, one for each row. And we're going to look at how the binary predictions compare to sort of the canonical predictions you expect if label 4 is the correct answer, or label 3 is the correct answer, or label 2 is the correct answer. And so we'll just count the number of times that there's a disagreement between the canonical predictions you would expect if 2 is the correct answer and what you actually observe. And we'll count the number of times that your observed predictions differ from 3 and from 4 and from 5 and 6 and k and so forth, right? And then we'll just choose the multi-class label, which has the smallest difference in terms of Hamming loss. So this is kind of coding theory is beautiful. It's something really nice which happens here. We have a bunch of binary predictions. Individually, each of these predictions is kind of sucky. I mean, it only tells us it's 1, 2, 3, or 5 or not. And it doesn't even do that reliably. And we're going to take all these partial predictions, which give us a little bit of information, and then we're going to combine them together and we'll get out the answer. So it's sort of a holistic approach. Here's where I describe how you do the prediction. So you have a bunch of binary predictions, and you just ask yourself which of these rows agrees, or which of these columns agrees with this column the best, and you measure the best in terms of just Hamming distance. And how many entries do you disagree? So let's see. In this case, for 1, we had disagreement, a disagreement, agree, disagree, agree, 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 agree. So that was 3 disagreements. You would add this up for each individual column, and you'd see which one is closest. Yeah?
So you intentionally add the dummy row and the column?
Oh yeah, it's kind of weird, isn't it? So this is actually not a dummy column. So it is possible that one of your labels is always in this, or always not in the subset, or always in the subset. This is a dummy row. And the correct prediction here is always black because for every label it's black, right? Yeah. It turns out there's a particular very nice code which we're going to be working with called the Hadamard Code. And the Hadamard Code has a row like that. It's stupid, actually. It's not very useful in practice. If you're actually implementing this, you wouldn't include that. But it doesn't hurt. It's a very simple classifier, which is great here. Okay. There's one other little note here, which is important. Sometimes you have 2 labels which have the same minimal number of disagreements, in which case you have to break ties somehow. And let's say you just break it randomly. Okay, so we're using this one classifier trick. So we're going to take the subset of labels and embed it into the feature space. And we're going to make this definition that the classifier for subset S is just C of x comma S. And we're going to have ecoc of the multi-class distribution denote B, the binary distribution, which is induced for this classifier. And then it turns out you can prove a theorem. The theorem says for every number of multi-class labels, there is a code such that for every binary classifier, for every multi-class distribution, 4 times the error rate of the binary classifier on the induced binary distribution bounds the multi-class error rate. The proof is actually very simple. If we go back to here, you can ask yourself, so suppose that I have some large value of k. How far apart can I make these columns? It turns out that you can make the columns differ in half the entries. So you can make it so that any two columns, any two multi-class labels, have a canonical binary prediction vector which disagrees in half the entries. I think that's actually true here. Let's see. Yeah, I think that's true here. So pick any two columns. The claim is that the number of disagreements should be at least half, in other words, 4. It turns out you can do this for any k. So if the number of disagreements is half of the number of binary problems, then the number of errors which an adversary has to induce in order for you to make an incorrect multi-class prediction will be 1/4 of the number of columns. And that 1/4 produces the 4 here. So is that clear? I claim the adversary must screw up at least 1/4 of the time in order to produce, on at least 1/4 of the binary problems, in order to induce a multi-class error. And that means that the multi-class error rate is at most 4 times the binary error rate. So you can actually constructively make these codes which have this large disagreement between two different columns. But there's a way to do it randomly, which is maybe very intuitive. All you do is you just create a random matrix where for every entry you just fill in a 0 or 1 at random independently. And the expected difference between two columns is going to be half of the length of the column. So I guess the general construction is called a Hadamard matrix. Let me actually show you. Well, I guess I'll show you later. Yeah. The Hadamard matrix is pretty fun. Okay. So this is kind of satisfying. It tells us that if we can find a small error rate binary classifier, then we can get a small error rate multi-class classifier, right? But there's a couple caveats which maybe make us think a little bit. This is not going to be interesting if the error rate is greater than 1/4 for the binary classifier, because 4 times 1/4 is 1, and saying my multi-class error rate is less than or equal to 1 is kind of not telling me anything interesting. I already knew that. There's also a problem with inconsistency. So the claim is there's a multi-class problem such that no matter what code you use, let's see, how do we look at this? So you have if you choose the binary classifier, which is the best possible binary classifier on the induced binary distribution, then the error rate, the multi-class error rate of ECOC using that classifier is greater than the minimum possible error rate. Right, so we have a multi-class distribution D. This multi-class distribution D induces a binary distribution. We can learn some classifier. Let's say that we learn the best possible classifier, right? So we succeed very well with our binary classifier technology that we have greatly refined. And it turns out that that does not imply you do very well in a multi-class situation. If you use the Equating output code with that best possible binary classifier, it's still worse than the best multi-class classifier. If you think about what this means mathematically, let's go back to the theorem. This is an error transform theorem. It says that some error rate bounds some error rate. It doesn't say that some regret bounds some regret. If we had a theorem of the form some regret bounds some other regret, or some binary regret bounds the multi-class regret, then we couldn't have this inconsistency result. So there's kind of there's a gap here. It turns out to be a repairable gap. There's a trick which lets us get a regret transform and eliminate the possibility that the best possible classifier does not induce the best possible multi-class classifier. Okay, so this is essentially how you can fix this. So you can take multi-class classification, and then instead of just reducing directly to binary, you can reduce to, let's try. Questions? You guys aren't asking enough questions.
How did you put those pictures?
One of my collaborators is Alina Begelsheimer, who finds and draws great pictures. Okay, so what we're going to do is we're going to reduce multi-class classification to binary probability estimation. So this is regression where the values happen to be either 0 or 1, right? And we're going to estimate the probability that y equals 1 given x. Then we're going to reduce that to just binary classification using the technique that we previously talked about. Okay. So now everything's going to be the same as before with error correcting output codes, except it's going to be a probabilistic error correcting output code. So the questions that we're going to be asking are, what is the probability that the label is 1 or 2? What is the probability that the label is 1 or 3? What is the probability that the label is 1 or 4? So we can apply the probing algorithm. We can get out these estimates of what the probability that y equals, the probability that the label is 1 or 2. Let's say the probing algorithm says 0.91. It says 0.55 for here and 0.46 for here. And then the way that we make a multi-class prediction is essentially the same, except now instead of using the Hamming distance between the predictions and the canonical predictions, we're going to use the L1 distance. So the L1 distance is between 0.91 and 1 is 0.09. The L1 distance between 0.55 and 1 is 0.45. 0.46 and 1 is 0.54. 0 and 0.55 is 0.55. You just figure out what the distance is, and you sum this up. You get 1.08. So and then you choose the best one, right? So it's exactly the same style as before. It's just that our notion of distance is changed because we have these continuous values. So the claim is, this fixes the problem. For this algorithm, we can prove a regret transform. And if you go and you actually apply this algorithm, it works better than error correcting output codes. So perhaps it doesn't surprise us, but I don't know, it surprises me at times. So I think I said at the start that the state of learning, of the theory of learning and the practice of learning, of machine learning, is not very well developed. That means that it's actually fairly common for theory to say one thing and practice to say another. But it seems like this is working here. So what's happening? So we have a bunch of different multi-class problems. And then what we're going to do is we're going to apply an error-correcting output code with a Hadamard code, some special matrix that I'll show you, and which we're going to apply the probabilistic error-correcting output code. And we're going to look at the error rate on the test set. And so I guess below this line here means that the error rate for the probabilistic error-correcting output code is smaller than the error rate for the error-correcting output code. And you see that it's below the line for almost all problems and almost all base algorithms. I support vector machine and decision tree and logistic regression. Okay, so question is, what can we prove exactly? So we're going to use this one classifier trick that we like so much. So, right, how does this go? Our binary classifier is going to be, we're going to be applying the probing and reduction, right? The probing and reduction has a threshold, which I guess we're calling P here, right? Except we're also doing the multi-class, we're also doing the error-correcting output code, which is defined by a subset. So for some subset, what is the probability that Y is in that subset, given these features X? So our S and P are going to be the names of our classifier. And then we're going to have some induced distribution on the binary problem. And now we're going to prove a theorem. The theorem says, for every number of multi-class predictions, there exists a code such that for every binary classifier, for every multi-class problem, okay, let's start here. The error rate of the binary classifier on the induced distribution minus the minimum possible error rate. So this is the binary regret that C suffers on the induced distribution. Take the square root, multiply by 4. The claim is that this bounds the multi-class regret. So the error rate of the multi-class classifier minus the minimum possible error rate. So in particular, what that says, if you think about it, is that we can't be suffering this problem. Because if our binary classifier is perfect, this difference is 0. Square root of 0 is 0. 4 times 0 is 0. So 0 is greater than or equal to the difference between the multi-class error rate and the best possible multi-class error rate, which has to be 0 because this guy is larger than that always. So it says that binary consistency implies multi-class consistency. It also says that when the binary error rate is 0.25, that could be okay. So in particular, maybe you just have a naturally noisy problem, and then the binary error rate is 0.25, but the minimum possible error rate is also 0.25, and then you must be getting the best possible multi-class predictor. All right, so here's the Hadamard matrix. So the matrix that you use is the Hadamard matrix. There's some other matrices you can use, but this is maybe the simplest one. The Hadamard matrix is I think I'm going too fast. Are there questions about this? Yeah?
So I'm trying to understand this. This is in an agnostic setting, so there's no assumption on the dependence of the errors between binary classifiers, right?
Right. Yeah. So the binary classifiers could err, and I guess when we're doing the analysis, we're going to be thinking that the binary classifiers are trying to conspire to cause a multi-class error. And the question is, how many of them have to err in order to cause a multi-class error? Okay, so that's the theorem, and the proof is reasonably straightforward. So step one in the proof is we're just going to choose a particular code. The code happens to be the Hadamard Code. The Hadamard Code is something which is very handy, and you should probably learn it because it'll just turn out to be useful at some other point in your life. So I guess the Hadamard Matrix, which defines the code, is recursively defined. Actually, I think I forgot the zeroth entry. The zeroth entry is just the 1-by-1 matrix, which has a 1. And then the way it goes is you replicate, negate. And then you replicate, negate. And then you replicate, negate. And then you replicate, negate. So this is a way of defining recursively the Hadamard matrix. And the claim is the distance between any two columns is at least half of the number of rows, which you can check if you want. It's true. I won't actually prove that. But nevertheless, it is true. Okay, so if B is the number of binary problems, so it's the number of rows, the distance between any two columns will be at least B over 2. So the way that we're going to work out how this works is we're first going to suppose that that the binary classifier is perfect. And we're going to see what that implies. And then we're going to think about what happens when the binary classifier is wrong. So suppose it is perfect. So then what we're going to do is going to think about the sum over the different rows of the probability that the set containing L, the probability that the set containing L given X is 1. So maybe we should go back to the Hadamard matrix. Let's just think about the first label, right? So it turns out that the first label is always in the set. And we'll just think about what's going to happen for the first label. And the claim is everything's kind of symmetric because somehow you can complement everything and it'll work out. So we're going to take the sum over the different rows of the probability that the set containing the multiclass label 1 contains the true label, given the features. Right, so let's say that our binary classifier is perfect. In that case, the output of this probability, of this call, is going to be the sum over the labels in the set containing label 1 of the probability of the label given X. And then there's a magic reordering trick. So we have a sum over binary problems and a sum over probabilities of label L prime given X. So it turns out that for the critical label, I guess, L, it's always going to appear in here because we're looking at the set containing L, right? So we have a term which is like the probability of L given X repeated B times. So it's B times the probability of L given X. And then for every other label L prime not equal to L, half the time it will appear here, and half the time it will not. And that's because of this. With a Hadamard code, the distance between two columns is exactly half of the number of rows. So that says that half the time. So I'm label 1. Let's go back to the matrix. I'm label 1. Label 2 is going to be in my set 1, 2, 3, 4 times out of 8. Label 3 will be in the set 1, 2, 3, 4 times out of 8. Same for all labels. So that means that there are B over 2 instances of labels, not of other labels. Right? And then this simplifies to be just this because this is the sum over all labels except for L of the probability of the label given X. You can take half of this and place it into this sum, and you have the sum over all labels of the probability of L given X. The sum of everything is 1. So you get the 1, and that's it. Okay, so this says that if our binary classifier is perfect, then this quantity here is going to be this quantity here. So this quantity here is kind of, it's very interesting because this is the probability of L given X plus 1 divided by 2 times B. So you know what B is, you know what 2 is, you know what 1 is. That means you can actually estimate the probability of L given X when the binary classifiers are perfect. So in particular, you could take this sum, you could divide by B, multiply by 2, and subtract 1. And that would be a prediction of this value. Okay, so that was all kind of under a caveat of suppose the classifiers are doing perfectly. We need to figure out what's going to happen when the classifiers are wrong, or at least wrong part of the time. So you can go back to the probing theorem, and you need to modify it slightly in order to get something that we can use. So I guess we had the probing theorem said that this squared was bounded by this. So we can take a square root of both sides. We can push the square root through the expectation, then we get this statement. So it says that the difference between our probability estimate and the true probability estimate is bounded by the square root of the binary regret. So we have this technique here for estimating the probability of L given X. And the question is, what is the most efficient mechanism for the adversary who, on a budget to disturb our estimate of the probability of L given X? So let's say that the adversary is going to try to make this sum here be epsilon times B larger than the truth. Then, because this is a square root, it turns out that it's more efficient for the adversary to mess up a little bit on each problem, mess up by just epsilon in the estimate of each individual problem, than to mess up a lot on one and very little on the others. So in particular, the adversary is going to want to make the difference between the truth and the estimate of the truth for each binary problem be just epsilon. Okay, so we have a technique here for estimating the probability of some particular label given x, right? We take this sum, we divide by b, we multiply by 2, and we subtract 1. If we have an adversary on some budget, the most efficient way for him to disturb this sum is by just changing each individual thing by some amount. And then if this adversary is going to be successful, he has to take, maybe I should draw this. So we have label 1, label 2, label 3, label 4, and so forth. Each of these has some particular probability. And then if the adversary wants to actually induce a multi-class error, he has to make our estimates of these probabilities be significantly off. So in particular, he has to reduce the estimate of this guy and increase the estimate of this guy in order to get us to choose 2 over 1. Right? So this quantity must be larger than this quantity. So this, the factor of b is kind of shared by everyone. The factor of 2 means that if this sum gets disturbed by epsilon times b, our estimate of this quantity is going to increase by 2 times epsilon, or decrease by 2 times epsilon. It can be disturbed by twice epsilon. And then if we're going to be forced to predict 2 rather than 1, so we have an adversary with a budget of epsilon times b. He can cause this probability estimate to decrease by twice epsilon, and simultaneously he can cause this probability to increase by 2 times epsilon. So this gap here, the gap in the probability between the class that we want to predict and the class that we actually predict can be as much as 4 times epsilon. So that's where this 4 times epsilon comes from. So this is actually the end of the proof. We have 4 times epsilon, and we already have these square roots here, so it's 4 times that square root, and that finishes the result. All right. Are there questions about this? Okay, so there's a simple extension. We know that when our binary classifier is correct, this sum equals this, using that reordering trick. And that means that instead of just predicting which multiclass prediction is correct, we could just estimate the probability of L given X. We could just output 2 times that particular sum for our probabilistic estimates divided by B minus 1. That can be handy at times. Sometimes this is the multi-class version of the probing algorithm in some sense. So in particular, you can prove that for every classifier, for every multi-class distribution, 4 times the binary classifier's regret bounds the squared error in our estimate of the probability. And of course, we won't go through the proof of this because we essentially already did, right? We have this peacock prime which is making the predictions, and it's just making predictions in this way. All right. So that's it for the simple multi-class classification problem. And then there's a variation on multi-class classification, which is sort of very flexible and handy at times. So this variation is called cost-sensitive classification, and I'll go through this next. So in cost-sensitive classification, we're going to have some measure on the features across k positive numbers. And I guess the question is, what do these numbers mean? What these numbers mean is, if you predict 3, then the third number is how much loss you'll pay. It's the cost. So this is cost-sensitive classification. So we're going to be learning a multi-class classifier. We're going to be training from features cross the cost vector. And we're going to be trying to find a classifier to minimize the expected cost-sensitive loss. So L vector is this set of positive real numbers, and we're going to pay the loss of whichever choice we make. This is a very general problem. Most problems can be, or I wouldn't say most, it's a little too strong. A large number of problems can be thought of as cost-sensitive classification. This is kind of the generalization of importance-weighted classification and multi-class classification, right? Each individual choice incurs some particular loss. The question is, can we reduce cost-sensitive classification to binary classification? And the answer is yes, of course. And it's essentially the same algorithm as what we talked about before. We're going to have some particular code matrix, and now what we're going to be estimating is instead of the probability of label 1 or 2, we're going to be estimating how much is the sum of costs of 1 and 2 divided by the sum of all costs. So we're going to do a regression problem, and we're going to predict what is the relative cost of labels 1 and 2. So how does this work? You have some cost-sensitive examples. You have your importance-weighted learning algorithm. We're going to have a bunch of subsets. Then we're going to have the sum of the costs over all the labels. We're going to have the sum of the costs of the losses for the labels in the subset. And the question is, for some particular feature, is the loss in the subset greater than some threshold times the total loss? And we'll have this importance weight, which you recognize from rubbing. And then, well, let's go one more. And then we're going to just predict the label which minimizes the expected cost. So how does this go? If y is in the subset and the classifier says yes, the sum of the cost in the subset is greater than t times the threshold, that's kind of bad for y, right? It suggests that y has a high cost. And if y is not in the subset and the classifier says no, that says that the complement set, which contains y, has a high cost. So we're going to take the expectation over the subsets and the thresholds of this quantity here. We take the minimum over y, and that's the multi-class prediction we'll make. This is essentially the same algorithm as before. It's just that we've modified it a little bit to be a little bit more flexible in the kind of information that it takes in. Okay. We're going to use the one classifier trick. We're going to use the costing reduction to get all the way down to binary classification. So we're going to train one particular classifier, and then that we can prove a theorem about this one classifier that we train. The theorem is for all k, for all numbers of multi-class labels, there's a code such that for all binary classifiers and for all cost-sensitive learning problems, see, this is the binary error rate on the induced problem minus the minimum possible binary error rate on the induced problem. So this is the binary regret times the expected sum of costs. Take the square root, multiply by 4, bounds the cost-sensitive regret. Almost the same as for the analysis for just probabilistic error correcting output codes, except now it's a little bit worse because we have this sum of costs. All right. I'm kind of getting tired, so I'll let you guys go through the proof. It's essentially the same proof as for probabilistic error correcting output codes. So there's a modification of this. Just like for probabilistic error correcting output codes, instead of making a hard prediction, you can make a soft prediction. So you can estimate the cost, the expected cost, or actually the expected relative cost of some particular label. So you can you can modify the output to predict this quantity for any particular label. So this is the expected cost of y. This is divided by the expected total cost, plus 1 divided by 2. Yeah. Well, you can actually estimate just this quantity here. All right. It's a hazard of skipping through something. And you get a regret transform for that, too. All right. So we actually haven't done any experiments for this reduction yet. I guess I have some expectation that it would work, but I guess the problem is, so the way things work in machine learning is there's a lot of data sets people have laying around. And the way that you maybe test that your algorithm is sane is you go out and you try your algorithm on these various data sets. And for a long time in machine learning, people were kind of focused on maybe classification or maybe regression, which meant that there were a lot of problems that were actually cost-sensitive classification that got turned into binary classification or just plain multi-class classification. Just because people didn't know how to think about cost-sensitive classification at the time they were looking at the problem. And then it's kind of awkward to go back after the fact and try to figure out what the costs are because you weren't the one who actually, you actually don't know. The information's kind of lost. So that's the reason why we haven't done any experiments. There's some other questions here. Which code do you use in practice? So the theorem says use the Hadamard code. And there's some other possible codes for which you could prove a similar theorem. It's not clear that amongst the codes that you can prove a good theorem, it's not clear which would be the best. And it's not even clear that... Okay, so one of the problems with recurring output codes is there's sort of a danger. The danger is maybe by creating these binary problems, perhaps at random or using some sort of dense code like a Hadamard, maybe you're creating hard binary problems. Where hard doesn't mean necessarily information theoretically hard. It just means that it's sort of computationally difficult or representationally difficult to make a good binary classifier, right? So if you go back and you look at all these theorems, you should always keep in mind that we're saying, a small binary regret implies a small cost-sensitive regret. The theorem doesn't actually say that you'll get a small binary regret. So this is a legitimate concern to have about this kind of approach. Yeah, all right. Okay. This approach is much newer than the approach that Sam talked about. It's a relatively new theory that we've been developing over the last few years. The limits on what are possible are not entirely known. So I guess tomorrow I'll be talking about reinforcement learning, which is sort of the grandmother of all learning problems. And there we're running into things that we just don't know how to reduce to binary classification, at least not right now. So it's not clear how far this can go. The other thing that I would mention is that it's pretty easy to play with these things if you want to. And things are changing quite a bit. So I gave some sort of tutorial on this at the last machine learning summer school in Chicago. I guess it wasn't really the last, but it's the last one in 2005. And since then, several things have changed. So, for example, I realized if you go and you look at the paper where this probing algorithm is published, it looks a bit different because, first of all, the importance weights were a little bit different, but they're equivalent to what I told you. And we're just talking about estimating the probability of a class. But it turns out that the algorithm just generalizes in a straightforward way to do regression. We figured out how to estimate quantiles. And there's a better cost-sensitive reduction analysis than is actually in this tutorial. So just recently, we figured out how to get something which depends upon. So let's go back. So this expected sum of costs is pretty unideal. It turns out that you can get a reduction which depends upon the difference between the maximum and the minimum cost, which is a big improvement. Okay, so that's kind of what's happened in the last year. So here's a pretty picture. So we talked about binary classification and importance-weighted classification. We know how to reduce to binary. We talked about regression, which we can reduce to importance-weighted classification, which we can reduce to binary, and multi-class, which can be reduced to regression, which can be reduced to importance-weighted, which can be reduced to classification. And we talked about a little bit about how to go directly from cost-sensitive classification to importance-weighted to binary. And in each of these, what you can do is you can say, suppose my classifier has some particular binary regret R. What does that induce in terms of the regret for multi-class classification? So it might be 4 times square root of R for multi-class classification. This new way to do cost-sensitive classification actually goes to multi-class, to regression, to importance-weighted, to classification. And then you get this, which is a little bit better than this. So cost-sensitive classification is a very general problem. In particular, you just think about it for a moment. You can have any loss function on some finite number of possibilities, and it's multi-class. It's a cost-sensitive classification problem. These two are equivalent to each other. Tomorrow I'll talk about how to reduce reinforcement learning, or at least some parts of reinforcement learning, to cost-sensitive classification. And I guess there's some other things here. Oh, there was quantile regression there, which we talked about briefly. Outlier detection is a little bit interesting to think about. There's some sense in which outlier detection can actually be solved by reduction, but not very convincing. Ranking is a very interesting problem. We just recently figured out how to reduce ranking to binary classification. So I told you that the probing approach doesn't work, but there is another approach which involves checking for pairs if the ordering of the pairs should be this way or that way. It turns out that if you do this right, so if you do this for all pairs, then you order according to the number of wins, you can actually prove some sort of regret transform. Oh, man. All right. Okay. I think I'm about done. There's several papers that I put in here which cover the material that I went through. Yeah. So, any questions? All right. Well, hurricane willing.
Let me try one.
Okay.
So according to your result, it's hard for me to see how the number of classes play a role in your PECOC reduction.
Right. So the number of classes is playing a role here because we have the expected sum of costs, and the number of the sum of costs is going to grow with the number of classes, or it may grow with the number of classes. But we just figured out a better reduction, which eliminates this dependence. So it's kind of counterintuitive. Yeah, it's a very odd thing about the theory. The theory says there's no dependence on k here, right? So the way that it could come in is it may be that as k grows, the regret tends to grow in practice. It may be. I don't know. It's kind of hard to measure these things. Another thing which is interesting to think about is, so there are other kinds of, there are other ways to reduce multiclass to binary. So for example, there's the all pairs reduction. In the all pairs reduction, what happens is you learn a predictor of is this class 1 or class 3? Is this class 1 or class 4? Is this class 1 or class 5? And so forth for all pairs of classes, right? So then you can go and you can prove a reduction. And the reduction that you end up proving is something like the binary regret times k minus 1 bounds the multi-class regret. So then you do have a dependence upon k. It's sort of mysterious that you can get rid of it here. I don't know what to say. All right. Any other questions?
Yes. At the beginning of your talk, you kind of motivated us by saying that it was working well in practice. And could you elaborate a little more just to tell us if it does really work in practice, and should we reduce all the problems? Besides the fact that it's elegant, is there cases where we shouldn't reduce? And there are specific algorithms for specific problems, so sometimes maybe it's interesting to reduce. So if you have some words about that.
So I would not be surprised to see the reductions approach fail when you have a small number of samples, because some of the things we're doing are not very sane when you have a small number of samples. Like when you rejection sample, if you rejection sample and you end up with one sample, it's kind of weird, right? So I think Sam likes to talk about sort of the straightforward, simple approaches which you should just try before you try to think at all. And if you have a reasonable amount of data, let's say 1,000 samples, and if you have some well-defined problem for which a reduction already exists, I think it's reasonable to just try this. It seems like it works. It's computationally efficient, and often you get performance which is as good or better than direct approaches. Especially if you encounter... Okay, so I think actually what I talked about today is not the most convincing case for applying reductions, because often I was doing things like reducing regression to binary classification. Regression is a pretty well-solved problem. People have a lot of different regressors. They work pretty well. If you look at the experimental results, you see that it worked, but it wasn't like convincingly better than other approaches people use for regression. It's when you encounter some problem that people haven't spent man lives working out how to solve, that I think this approach works the best, because you get one reduction from this new problem to some core technology that you know about, and then that one reduction implies a lot of different algorithms for trying to solve this problem. So it's just kind of an efficient approach in terms of the amount of time you have to spend thinking to solve some very new problem. Okay. Thank you.